Hi, AP Physics. Today we're going to take a look at power, and power is the rate at which work is done or the rate at which energy is expended. When we talk about power, the most basic fundamental way to define power is looking at work divided by time. Power is the rate at which work is done. We're also going to look at work. It's very important to look at work as a scalar quantity. Up to now, for the previous few units, we've been looking at a lot at vector quantities where direction is important. For power, as well as you saw, for energy, direction is not relevant to how much power is being expended when something is being done. Mathematically, we can determine power in a number of different ways. We can look at the work that's being done divided by time. We could also look at the force times displacement divided by time, force times displacement being the work that's done divided by time. So we're sort of breaking that equation down a little bit. And the final way to look at it, and this happens very often, is we can look at the force that's being applied to something times the velocity at which it's going to. D over T is your velocity, so force times velocity will also give you power. These terms, work, force, displacement, velocity, are terms we're very familiar with. P being the power, W being the work, force being the velocity, or F being force, D being displacement, and the V being the average velocity. When we talk about the units of power is the watts. A watt has the symbol capital W, and I don't want you to confuse this with the capital W that we use for energy. They're different terms, and it can be somewhat confusing because within the energy unit, we talk about power with the unit of W, right? And we talk about energy or work being done with the symbol capital W. So just be careful when you see that capital W, if you're looking at a unit or whether you're looking at a symbol. When we talk about a watt, what a watt is, it is a joule per second. Now, not every scenario we're going to look at is going to have our work being done or the power being expended as being constant. If you have a variable amount of work that's being done over a period of time, the power that's being expended is also going to vary as the work varies. If we get to this variable rate of work and energy being expended, our calculations of what power is being developed is going to be depending on the differential equation, the differential of work with respect to time, or the differential of energy with respect to time. And these two are equal from the work energy theorem, because we know that the work being done on something is going to be equal to the change in energy that it's experiencing. So we can look at this as from a calculus perspective, and this allows us to look at how much power is being developed at any particular time, and we don't have to rely solely on averages. So let's go through an example of this. This example is going to be an algebraic example, not a calculus example. And what we want to figure out is if we have a height that we want to lift something up with a particular motor. This motor has a power rating of 20.4 watts, and we're lifting up a 5-kilogram stone. We want to bring that up vertically as far as we can in 10 seconds. So now we have a couple of inputs. Now, the one thing that is missing here is when we talk about a 5-kilogram stone and we're lifting it, we're going to be working against gravity. But they don't tell us the weight of the stone. So our very first step here is to figure out what this weight is. We're going to want to find out how much work is being done. And to do that, we need the force that we're acting against. In this case, it's going to be the weight of the stone. And the force of gravity of the stone is going to be its mass times acceleration due to gravity, which is 5 kilograms times 9.8, and it gives us a weight of the stone of 49 newtons. And once we've converted this vertically moving stone into weight, now we have a power, a force, a time, and we're looking for the vertical height, which is the displacement. So looking at our power equation, we have the variables that fit this expression. Power is equal to force times displacement divided by time. And plugging in our values, we can say that 20.4 watts of power, and that's the power of the motor, is going to lift a 49 Newton weight in 10 seconds. How far? And then finally solving for the height, we'll find that it brings it to a height of 4.16 meters. Now in the next couple slides, you have a couple of examples that you see in your notes. You could try those in your notes and answer into the Nearpod. After them, you'll see that you'll have the answers after them, so you can check against your work. And then you'll see a CAS Learning assignment. I want you to try the CAS Learning assignment, make sure that all makes sense, and then you should be all set with the section.